figured it out. So variance of beta cap would both be variance of x transpose y, right, and x transpose x inverse. Now what will happen here is I have this, then this basically will become this, right, and then this will become this, right. So after that what happens is, yes, after that what happens is x transpose x beta plus x transpose x transpose x inverse u. What we do know is variance of u is this. This is something that we know. Now what will happen to the rest of this would be, this will become 0, the whole expression. This will basically turn out like x transpose x square over square, we square this, then we square this x, and x x to x transpose inverse square of this thing and variance of u. So we squared this term, we squared this term. Now this 1 will get into 1, so we will be left with this and 1 of that. This is how it will become to be my variance of beta cap, right? Yeah. Now this would also, if I have to say, wait, this would be not, no, yeah, let's do that later. Now in this case r square will be again explained variation about total variation. So this will basically become beta 2 summation yi x 2i plus beta 3 cap summation yi x 3i. Total variation is given by summation yi square. So this is my r square in this case, in my multiple variable case. Now that we know this was my coefficient of determination, now we will move ahead, right? We will move ahead to other things, like in simple words this can also be written as 1 minus RSS over TSS, that is 1 minus summation ui cap square summation yi square, right? Now I have another thing called adjusted r square. This is adjusted r square, right? Now adjusted r square is what is going to be considered first. Adjusted r square is basically adjusted for degrees of freedom, right? So this would mean if my r square was this or this, I will adjust them for their respective degrees of freedom. In current case, in this case, it will basically become something like 1 minus summation ui cap square k minus 1. Sorry, no, that will be for that. Wait, this will become n minus k, and this will be this is, wait, one thing I have a doubt in right now. Oh wait, I have to confirm a thing. Oh, I have to, just 1 second, it will take. Okay. Yeah. So it will not be this. Wait, yeah. That was correct. Yeah. Wait. So in any variation case, this is my explained variation. This is my residual variation, and this is my total variation. So here what I just did was wrong. It will go like this here. Again, out of habit I wrote it this time. Wait. Yes, this will go and become like n minus 1. So this was my basic idea of this, right? This, and in this case, what my adjusted for this one, what will my adjusted degrees of freedom look like? Summation yi cap whole square upon summation yi square. This would be k minus 1. This would be n minus 1. Yes, right. So this is my adjusted degrees of freedom. Adjusted r square, right? What is the relevance here is, let us wait, why adjusted r square is needed to provide a more realistic goodness of it, unlike r square, which is always, yeah, r squared will always increase the same when independent variables, penalizes extra values, detects useless variable, avoids overfitting, more realistic assessment. Okay. Provides a more accurate measure with multiple. Yeah. So what is my thing? I now understand better. So my r square will rise if there are more variables in my model, Because as the number of variables will increase, like x1, x2, xn, my explained variation will automatically increase. What does that mean? If my explained variation has increased, my RSS r square will definitely increase. But adjusted r square, because it's adjusted for degrees of freedom, any addition of new variable won't change its value unnecessarily. It might change its value if it's an important change, but otherwise it wouldn't change its value unnecessarily. Yeah. So it will only improve when model improves more than would be expected by chance. So it will only increase, right? That's the difference between my adjusted r square and other r square. Now going ahead would be my relationship between r square and adjusted r square. Now I know my adjusted r square I just discussed. It was something like this right here. Right. Now what can I put here for it to be? It would basically can also be written from this is yeah, so this is what it can be written. Now wait, what we discussed yesterday or in the last previous videos was that r square is equal to explained upon total variation. That would also mean 1 minus RSS upon TSS. That would also mean RSS by TSS is also equal to 1 minus r square. So I can basically put 1 minus r square here. My r looks a little like k, so ignore that. But that is the relationship between my adjusted r square and my actual r square. Right. Now from this I can derive two conclusions. For k greater than 1, is adjusted r square less than k greater than 1. Sorry. I made it wrong. Wait, that I got confused by my own handwriting right now. So, yeah, my k is greater than 1. That would lead to my my numerator will be greater. This will be greater. That would mean if it's greater than 1, then my denominator will be less. Right? See, r square, adjusted r square, all of them are between 0 to 1 only. So if I'm saying, because this is square, it's always between 0 to 1 only. So that's not my confusion. So in this case, it will be simple general conclusion. This is greater than 1, so this will become great. This great becomes great. That means I'll have to subtract a higher value item. This will be this item as a whole will be greater than 1. So whatever I'm multiplying with this will be also greater than this value or equal to this value. So if it's greater than or equal to this value, that means this is going to be smaller. Now, r square can be negative also in these adjusted r square, but r square is always positive. That difference is also there. Now, moving ahead. It's quite a random deduction, it seems like, but it is not. And the more you analyze it, the more it will be like, okay, it's not. So just kind of keep looking into it, and you might as well find some answers out of things which I don't have right now, but eventually all of us will have a better clarity out of these things. I need a thicker pen. That doesn't. So we have basically, for a model like this, we have calculated all the values. We have calculated beta 2 would be 2 fat weight. Maybe it's 7. Beta 2 will be something like summation yi x2i summation x3i whole square minus summation yi x3i x2i 3i. Yes, then this, sorry, yes, x2i square x3i square minus summation x2i x3i whole square, right? Similarly for beta 3 and for beta 1 I will write to be so this is how it will go. Now beta 3 formula you can write, it's symmetrical to this only, so wherever it's 2 you put 3 and wherever it's 3 you put x. So, and you can also refer my last video for that, one of the last videos definitely. Now what is important was here to discuss variance of beta. Variance of beta was 1 minus this r23 square summation x2i square. Similarly, variance of beta 3 goes like so this would be my variance, and yeah, that would be my that. Now I'm going to do one more new topic, so that will be quite interesting to do. That's multi collinearity. Right, so this will be multi-collinearity. What does that mean? Existence of perfect or near perfect, that would mean imperfect relationship among some or all of the regressors in a multiple regression model. So a perfect relationship would mean x1 lambda 1 x1 lambda 2 x2 up until lambda k xk is equal to 0. An imperfect relationship would mean x1 lambda 2 x2 lambda k xk plus v is equal to 0. So this error term, existence of this error term is what changes things, right? So yeah, now what are my implications among the both cases? So if I have perfect multicollinearity, that would basically result in my x variables being indeterminate. That would also mean my standard errors are infinite. In case of imperfect, my this is there's a relationship here between them, which is why my coefficients will be indeterminate and my standard errors will be infinite. In imperfect multicollinearity, what happens is they share an imperfect relationship. So although my coefficients would be determined, they will still possess large standard errors, leading to inaccurate results and failed tests. So these are my two cases, and this is what happens in both these cases. Now what happens is the examiner, if were to ask you if the examiner were to ask you about imperfect multicollinearity and its consequences, what are the basic consequences that will arise out of it is basically the variables. What happens is OLS estimators are still blue. That means they are linear, unbiased, efficient. Minimum variance also is there. That is, in this case, they are linear, they are unbiased, and minimum variance is also there, right? Yes, but what is still missing is what the problem would be. R square will be too high, and standard errors will be too high, due to which my t will be insignificant. So you see, my minimum variance of beta is correct. It's not like it is wrong. But the issue here is still with my standard error. Standard error was this. This is my standard error. This is my variance. So this will still be minimum. But this will be my problem creating thing. So that will be my giveaway here. Right. Now what are my sources of this issue are data collection, then constraints can be a problem, then misspecification, then overdetermined model, and then time series data issues. So that all those can be my issues. Now other things about is detecting multicollinearity. First we discuss right now R square too high and insignificant t's, right? Other would be my variance inflating factor and tolerance variables. Now variance inflating factor is the degree to which an estimate variance of an estimator is inflated due to presence of multicollinearity. So this is basically this. We just did one thing, right, which was variance of beta. It went like beta 2 this over this. That would mean this is my VIF. Now practically if you see, if my VIF is high, that means R23 was high, due to which my variance is high, due to which my this became high. So yes, yeah, so R23 approaches 1, VIF approaches infinity. R23 approaches 0, VIF approaches 1. Similarly, inverse of my variance inflating factor is my tolerance value. Since this have direct relationship, this will have my inverse relationship. So I can be mistaking things at some point. I take no guarantee. It's just a revision thing that I'm doing for myself, with a definite idea that nobody's ending up watching this. So don't really reach me if things are not up to the mark here. So this is 1, if then 1 1 0. So my tolerance value will be 0. If this is 0, then my tolerance value would be 1. So this, then the third method of detecting will be auxiliary regression. That would mean regressing each xi on remaining values and obtaining respective Ri squares. Right, so this would mean I'll use my F test here to test. First I'll take this. Then I'll do this. Same x1, x2, xk n minus k plus 1. So this will be my that, and this will be my relationship. That is that. Now fourth point would be for our global test. It is one of my favorite things to ever exist. Hopefully I don't forget this on exam day ever. So it's a battery of 3 tests. First test is chi-square test. Chi-square test is to determine that there is multicorrelation or not, to check the severity of multicollinearity as a function of explanator variable. So H0 will be variables are orthogonal. H1 would be H0 is not true. Right. That is, they are collinear or related. This was mean they are not related. So my standardized correlation determinant would be 1 R23 R23 1, and my test statistic would be, because I have already mentioned it's a chi-square test, my under H0 test would be modified chi-square is equal to minus n minus 1 by 2k plus 5 log e 1 R23 R23 1 4 degrees of freedom k by 2 k minus 1. If chi-square is greater than chi-square 0.5, then we reject H0, otherwise do not reject. In this case of rejection, only multicollinearity exists. Now my part 2 is find location of multicollinearity using auxiliary regression. Right, so that can be used by the same thing that we just discussed. And then third would be pattern of multicollinearity. That would be to test H0 whether Rij is equal to 0 for all I not equal to j from 2 to k against H1 Rij not equal to 0. Similar things. If h naught is accepted, that means no multi. If h1 is rejected, h naught is rejected, then means multi collinearity exists. So that's my first part. Now there's also one more method which is scattered plot, but I'm not writing that. There are several remedial measures of multicollinearity. I'll just write them as they are. First is a priori information. Second would be pooling cross-sectional and time series data. Third would be dropping variables. This can lead to some other issues which we will discuss later in later videos. Then transformation of variables, that is two ways. First difference is good, but it can lead to autocorrelation. Then we can do ratio method, but that can lead to heterozygosity. So those two we can do, but they might have their own issues. So we'll have to confirm that whenever we do. Then addition of new data can also, then also PCA, principal component analysis, factor analysis, ridge regression lines, orthogonal polynomial, all of these methods can also be used.